The original laws of physics, those that we all know, are called classical mechanics, or Newton's laws of motion.
In the early 20th century, a new scientist came along named Albert Einstein. His ideas of general and special relativity revolutionized the world of physics.
In Einstein's theory of relativity, reference frames are used to specify the relationship between a moving observer and the phenomena under observation.
In relativity, unlike classical mechanics, time and space are thought to be as being relative to the observer. The only thing that remains constant is the speed of light.
The concept of relativity is fairly simple.
As you can see by this diagram we have drawn, two objects are moving in the same direction at different speeds. Object A is moving at a constant velocity of 5 meters per second, and object B is moving at a constant velocity of 3 meters per second.
The relative velocity of object A in the frame of reference of object B is 2 meters per second, and the relative velocity of object B in the frame of reference of object A is negative 2 meters per second.
The concept of relativity is the main difference between Einstein's theories and Newton's laws. Another difference is the cause of gravity. Einstein believed that gravity was merely a geometric property caused by the curvature of spacetime.
The special theory of relativity has two postulates. The first is that the laws of physics are the same from all frames of reference. The second is that the speed of light is the same from all frames of reference. This further separates Einstein's theories from Newton's theories.
The first postulate is very simple. No matter what frame of reference an observer is in, the laws of physics remain the same. The second postulate is more complicated and difficult to comprehend. However, it is simply a property of light. Allow me to demonstrate.
If it were possible for a spaceship to move at 99% of the speed of light, the relative speed of light to the observer is still c, or the speed of light. In other words, the speed of light always remains constant. This was the basis of a thought experiment that Einstein developed when he was only 16 years old.
This idea of a constant speed of light is ultimately what led to Einstein's theory of relativity.
Another revolutionary idea that Einstein developed was the energy-mass equivalence. He demonstrated this with his famous equation E equals mc squared. By this equation, Einstein was able to demonstrate an equivalence between energy and mass. In other words, as you put more energy into something, its mass increases. Mass can also be converted to energy. For example, if 1 gram of matter could be converted entirely into energy, the value of the energy produced at 10 cents per kilowatt hour would be about $25 million. Furthermore, due to the conversion of mass to energy, the sun loses about 341,000 kilograms of mass per day. If the sun were 2 times 10 to the 30th power kilograms, it would last about 8 times 10 to the 19th years longer, which is much longer than current projections for the lifetime of the sun. Another concept in special relativity is simultaneity. This, along with the constant speed of light, provides the basis of special relativity.
Simultaneity is the idea of two events happening at the same time in a frame of reference. According to the theory of relativity, there is no absolute relation between events. What is simultaneous in one frame of reference is not in the other.
Here are Einstein's equations of special relativity. The first idea that these equations demonstrate is time dilation. As the spaceship approaches the speed of light, time slows down. So when a spaceship is going very fast, the Earth appears much closer to the star that it's headed to from the frame of reference of the occupants. The speed computed by the spaceship will also be slower because time appears to be moving slower from their frame of reference. The reason for that is explained by another thought experiment that was developed by scientists in the early 20th century. So there's a spaceship with a beam of light bouncing up and down from the top and bottom. As this moves through space, it would appear that the speed of light is slowing down in order to reach the top of the spaceship. However, that can't be, so the only explanation to fit in with a constant speed of light is that time itself is slowing down.
Here we have a graph showing that as energy increases, mass increases as well. This shows us that E is equal to mc squared, an equation that Einstein developed. Energy equals mass times the speed of light squared. As mass increases and energy increases, as the speed of the object increases on the graph, energy also increases as well as mass. going up and up and up until it reaches the speed of light, which we cannot reach the speed of light because energy is equal to mass times the speed of light, which is impossible.
According to the relativistic factor here, if you were to get an object up to the speed of light, you would have to divide by 0, and that won't work, and so that's why
Exactly.
the speed of light is the universal speed limit. Relativistic effects start showing up when an object is going around 0.35 or 35% the speed of light. However, the fastest we've ever been able to go is about 9% the speed of light, which is how fast the space shuttle is going. And the speed of light is the universal speed limit. As Einstein's special relativity states, it is impossible to travel at the speed of light. We also learned that time passes differently for observers who see motion in a different way.
At non-relativistic speeds, a journey in the space shuttle to the nearest star, which is about 4.5 light years away, would take about 165,000 years. However, traveling near the speed of light, let's say 99.99% the speed of light, the space shuttle, from its own frame of reference, would not take nearly as long due to time dilation and length contraction.
Length contraction is simple. Here we have the equation for length contraction. As you can see, it's set up pretty similar to time dilation and the mass increase, and it functions in the same way due to the travel of light through the spaceship that I mentioned earlier. As an object approaches the speed of light, it shortens. So if we were to graph this out, it would be the inverse of this, and this would allow objects traveling in space to travel much less distance to the same object as it would if it were traveling at non-relativistic speeds. Einstein went on to develop his theory of general relativity.
The main difference between special and general relativity is that general relativity includes gravity, where special relativity does not.
In a nutshell, in general relativity, gravitation is caused by the curvature of space-time.
This equation replaced Newton's law of universal gravitation.
It provides a better explanation of the force of gravity than Newton's mechanics. In conclusion, the addition of frames of reference to Newton's theories led to the development of Einstein's theory of relativity, which allows for bizarre phenomena like time dilation, length contraction, and mass energy equivalence.
Furthermore, Einstein developed a new theory of gravity. Einstein's theories of relativity revolutionized the field of physics for decades and maybe even centuries to come.